In my previous presentations, I introduced the SIR model and showed how self-quarantine and forced quarantine change the shape of the epidemic curve. This time, I'm going to use Excel spreadsheets to model the epidemic. Excel makes it easy to visualize changes to the epidemic curve as a community would implement policies such as physical or social distancing, quarantine, and then also we can explore changes in other factors. This is the spreadsheet that I've been using for the videos that I already produced. You see the classic epidemic curve here in yellowish, and this is an unmitigated rise in infections brought about by introducing one sick person into the U.S. population on the 20th of January. By unmitigated, it means we do nothing. We just let it happen. And we've already talked about how we have this exponential rise to a peak number of infections. The spreadsheet picks these things out for me. You'll notice that the maximum number of infections, if you do nothing, is going to be 220 million, and that will occur on May 26th. We would lose 2 million people by the end of the year, and we would have 44 million people hospitalized at the peak. So that would be at this peak infection right here, which occurs on May 26th. Now, I also include a box up here that has other input parameters. You may recall from my other videos that I introduced the transmissivity by fitting to data from South Korea. This recovery term I also fitted to data from South Korea, and the mortality rate, which is just 0.6%. Now, that's still 6 times the seasonal flu, so it's nothing to scoff at. I have two other terms that I can enter into this spreadsheet. They are this term F1, which is the fraction of the population that engages in self-distancing. F2 is the fraction of the population who is forced into quarantine because they are showing symptoms or have tested positive for the infection. You will notice that I also have a date of self-quarantine. That's when the government or your municipality suggests, hey, let's all self-quarantine, let's stay home. And the duration of that self-quarantine is in the cell right below it. That's how many days you're going to engage in it. Over here in column T, we also introduce the population of the country, city, or state that you are concerned with. Let's use our spreadsheet to explore the effect of social distancing. 2 weeks back, on the 16th of March, there was a nationwide self-distancing policy put in place by the president. Let's assume that it started on the 16th of March, was set to last 15 days, and 50% of the population actually abided by that. What you see happening is that the red dots represent the unmitigated infection rise. The orange dots or yellow dots represent what would happen if all we did was social distance. You see that what it did is it pushes the peak off to the right. It buys you time, but it doesn't change the magnitude of the peak. Suppose we extend that to 30 days. Well, what's it going to do? It just pushes it further to the right. And you can imagine if we just keep extending it, it's just pushing the peak further to the right. And so all that is doing is buying us time. If we don't aggressively quarantine, time alone will not be enough. So instead of just having aggressive social distancing, we also need to quarantine. The best way to visualize this flattening of the curve is to go ahead and choose the implementation of social distancing a little bit later in time. So it's happening during the exponential increase in the number of infections. So let's go ahead and change this date. Instead of March, let's change it to May 16th, and let's do it for 30 days. So what you see happening there is that by making it May 16th, we were going up the high infection rate of the unmitigated response. We turned the corner and it dropped, came down, and then we relax after 30 days and the peak rises again. The peak is smaller than the first peak, but nonetheless, if you relax it after 30 days, you still get an increase in the number of infections. Well, let's move this back even further. Let's move it back to May 4th and see what it looks like. Well, this is the thing that's classically thought of as the flattening of the curve. If you implement on May 4th this self-quarantine in here, what happens is you begin to roll over and flatten what would otherwise be this red exponential increase. And then it begins to roll over, and then, because you let it only last 30 days, you release everybody back out into the workforce. They're circulating with infected people. The infection rate rises again. Well, let's see what happens if we extend that time to 60 days. Exactly what you can imagine happening. That is, we lower the rate of infection. In fact, in this case, we drop it down rather dramatically. We send everybody back to work, and we get this second peak that occurs. Now, this is occurring precisely because we are not testing and isolating infected people. If, in addition to social distancing, we implement an aggressive testing strategy so that we can isolate those who are testing positive, we change this rather dramatically. The more people we engage in social distancing, the more we push these things away to the right, the more aggressively we quarantine individuals who exhibit symptoms or test positively, the more aggressively we change the location and the magnitude of the peak number of infections. What we showed through these examples is that physical distancing is just one piece of the strategy. This social or physical distancing buys time by removing potential susceptible members from the pool of people who could get infected. Quarantine reduces the number of infected people who can circulate with the uninfected. And testing complements both of these. The results presented here show clearly that the best way to change the shape of that infection curve is to quarantine infected people. The problem is you got to know who's infected in order to do that. You could just simply quarantine anyone who's clearly exhibiting symptoms that look like they might have the coronavirus. That would be quite an aggressive strategy, but that's a perfectly legitimate one. Or you can test exposed individuals. This is classically what the epidemiologists do. They do contact tracing, and they test and they isolate all those who may have been exposed.